Hello again. We continue with the Renewable Energy Technology course, the lecture on geothermal energy, quickly moving towards the second section about what we actually do with the resource and how it affects the environment. The way we mine geothermal heat is that we use the stored heat in the rocks closest to the Earth's surface, the places that we actually can physically reach. It is being replenished continuously by the hot interior of the Earth, but that heat is conducting through a very thick layer of solidified rocks, and which actually insulate it. What we can do really is just use those hot rocks, and we're not really reaching the real source of the heat. We're just using an intermediate storage of that heat. We can certainly deplete the reservoir, that is, cool down the rock. We will not deplete the real source of the heat, but we can, if we utilize it too much, actually cool down a specific area, the one that we really reach in order to extract the heat. And again, the way we can most economically extract this heat is to rely on water. Water seeping through, that is precipitating water, seeping through the different layers of rocks, preferably permeable rocks definitely, and then being hauled up beneath some impermeable or cap rock in order to create a hot reservoir. The moment we reach to that reservoir, we will have a quite inexhaustible resource of hot fluid. It presents itself to us in terms of several ways, and the easiest way to imagine it is, first of all, a hot spring. This is what happens if the water finds a fracture or a crack through the impermeable rock and reaches the surface. Hot springs are the most common effect of geothermal energy reaching the Earth's surface. In certain places, geysers or fumaroles may also reach the surface, very, very few places, but they actually show that water can also evaporate inside in the trapped reservoir of hot rocks, and real steam is reaching us, not just water. If we penetrate through the cap rock, we will be targeting definitely to reach the best position, supposedly taking just dry superheated steam if possible, or if not possible, just drawing out the hot water and doing something with it. This is the most easy to imagine way how a reservoir of heat would be replenished with a vector or a heating carrier. That would be water and steam, and how we would be supposed to reach it, hopefully not too deep. When it comes to the quality and the type of those reservoirs, we can divide them in three different types basically: low enthalpy, mid enthalpy, and high enthalpy. It comes to temperature really, but not only temperature, because the pressure in those areas beneath the Earth's surface is also important, and this is what would give us the heat content of the water and steam, or any kind of fluid that can reach those areas and then come back to us to carry the heat. It is, well, not unanimously decided how really to divide the temperatures or the enthalpy values for the available hot fields. Generally, low enthalpy is being believed to be below 150 degrees source. Intermediate enthalpy anywhere between 150 Celsius to 200 something, and high enthalpy well above 200, supposedly all the way up to 300 degrees water, saturated water, or dry steam. The types of the sources. The easiest to imagine is that there is a solid rock under the Earth's surface, maybe not even permeable, quite impossible for the water to penetrate. If we can reach it and if we can extract the heat by some way, that would be perfect, because those dry, hot rocks, they are literally everywhere beneath the Earth's surface. At different depths, yes, but everywhere. At certain places, and these are exactly the resources that we are economically utilizing now, simply hot water appears or can be reached at economic depths. We call those hydrothermal resources. It could be saturated water, liquid dominated, or partially evaporated, in between saturated liquid and saturated steam. Other fields are called geopressurized fields, and those very often are being found simply by chance when drilling for oil or natural gas. It is pretty much the same type of drilling processes that are employed by when searching for the geothermal source. And in two quite notable examples around Paris in France and in Hungary in the Pannonian Plain, people in the old days, in the 60s and 70s, drilling massively for oil and gas, searching for natural gas fields, actually found lots of hot water, comparatively shallow, a few kilometers beneath the surface, comparatively good resources, more than 100 degrees hot water in quite good flows possible. However, that water is trapped in pretty complex structures, maybe together with hydrocarbons in shale rocks and so on. So the geopressurized fluids are not really easy to handle like the hydrothermal, simply hot water. They might contain salts, gases and so on, and usually they are used only for heating purposes. Then definitely if we reach inside volcanoes to the really hot interior, that would be the best choice, but it's almost practically impossible to do that, and definitely very difficult to send water there to extract the heat. Another option in volcanic areas would be to rely definitely on one concentrated spot of thermal source, which reaches all the way to the volcano top. However, the volcano itself is a very difficult area to explore. We still rely on water precipitating and then seeping through the ground to carry the heat to us. But we would be drilling slightly beside those areas, relying on the fact and researching carefully before the drilling begins what or where the temperature isotherms are lying. So hopefully reaching a decently high temperatures at a comparatively long distance from the exact hot spot. This is simply a representation of how the situation would look like. The hot dry rock resources should properly be called actually enhanced or engineered systems, because then we do not have the chance to extract directly hot water from beneath the surface, but somehow the drilling needs to reach down to the warm area, send some fluid, that would be water, and then extract it, but create or engineer the reservoir by probably cracking the rock so that the flow can start from the injection well towards the production well, then extract the fluid and run a pretty standard geothermal extraction system. Hot rocks are usually much crystalline, solidified rocks, difficult to penetrate, difficult to drill through, and very difficult to create the proper fluid flow with the proper high mass flows. Long exploration is necessary before drilling begins, and the exploration can be done in different ways. Easiest and the first step would definitely be to explore the outer surface. What kind of springs there are in the area, what kind of water comes out to the surface, the chemistry of that water, dissolved salts, dissolved gases and so on. All hot springs are actually quite mineralized. They tell a lot about where they pass through, what layers of rocks they're actually reaching or going through before reaching the surface. And on the basis of dissolved salts and minerals and gases in the water, actually the geothermometry science has been developed, just following what has happened with the salts, because when the water reaches the surface, it cools down gradually, and those salts precipitate. They start to crystallize, to get away from the water. And following that history, So certain investigations can be done theoretically on the history or what the temperature would be down beneath the surface for that water spring. The physical inspection of the Earth's surface can be done in several ways again, by the porosity of the soil or the rock beneath it, that is gravitational measurements, seismic measurements, magnetic measurements, electrical and electromagnetic, measuring in different ways, different structures, on how the structures are layered beneath the surface, and what might they promise in terms of possible to penetrate presence of natural aquifers and so on. Then, when actually the exploration begins, first of all, modeling is being done. The first drilling wells will try to confirm those models. Then measurements on what is being extracted are started. So now, once reaching really deep down and extracting some water, we can measure it again, do all kinds of tests, maybe do some fracturing beneath the surface and find out what is going on, whether the resource is promising or not. In general terms, please look at this picture. It is believed that approximately 40 degrees Celsius growth of temperature with depth, a kilometer of depth, is feasible for practical exploration. It is not possible to drill very deep. The current technological limit for drilling lies around 10 kilometers. And the economic limit for drilling is approximately around 6 kilometers. If we do not reach any feasible resource to that depth, actually there is no point of continuing the exploration. And the goal definitely should be that we reach a very valuable resource already at a few kilometers of depth. The geothermal energy definitely also has large environmental impacts as everything else, including all other types of renewable energy sources. However, regarding geothermal use, we actually reach down under the earth. We are extracting water that has passed through different layers of rocks, highly mineralized, also dissolving gases, and so on. And the processes of exploration and power plant development also involved additional work that might create noise, create different residues that need to be disposed of. If we start depleting the reservoir, certain seismic effects may start, and so on. The best example of gases and minerals being dissolved in the waters extracted from the underground are CO2 itself, hydrogen sulfide, very dangerous acidic gas, ammonia, nitrogen, radon, carrying radioactivity, boron, mercury and its compounds, silicium dioxide, carbonate salts, and then different halogenic and alkali elements. All of them can be found, and many more dissolved in the water. The moment we try to convert this water into steam, of course, we would have most of those gases coming out in the gaseous phase. Non-condensable gases, we call them. They mess up with the utilization processes for the geothermal water, and they are pollutants. Not only pollutants, but some of them are very potent greenhouse gases, not the least carbon dioxide itself. High salt content, actually we extract in most cases brine, very salty liquid from the ground. It is very corrosive, very difficult to handle, and those salt deposits may start easily to precipitate when the water cools down. Other environmental aspects would involve the pollution from brines being released or disposed of at the Earth's surface, maybe just discharged in natural waterways and changing the natural chemistry at the Earth's surface. So reinjection of fluids, absolute must. Reinjection of fluids should always be practiced. The moment something is extracted from the Earth in terms of hot water and the heat utilized, it needs to be returned back to the underground. This is the best way to treat it. Land subsidence may occur if the reservoir of water, the aquifer under the surface, is depleted too quickly. Induced seismicity may also be the result of this, including the result of re-injecting not in the proper way the fluid back under the earth, and definitely noise from different sources. Regarding carbon dioxide as the most representative emission from the geothermal sources and the most representative greenhouse gas, we can actually look at the fact that carbon dioxide is a pretty natural phenomena in most of the volcanic areas. Some of the large volcanoes are actually spewing out carbon dioxide constantly in enormous amounts. We can here, well, I do not totally agree with the authors of this chart, but we can compare what's happening from certain volcanic areas and a typical power plant, all of them together as a total global effect, kilograms of CO2 per year. And then come up to actually geothermal plants, man-made. So these would be actually the emissions provoked or involved with man-made geothermal exploration and utilization of resources. They are much, much, much lower, not only compared to the natural emissions of carbon dioxide from volcanoes, but also to all kinds of fossil-based power generation. This is another example. Not the exact figures, definitely. We can talk about that a lot, but simply the relative comparison of geothermal emitted carbon dioxide, for example, when flushing a geothermal fluid, and fossil-fired power stations. Regarding costs, we can say that the initial costs involved in exploration and utilization of geothermal projects or systems are pretty high. Already before we start to exploit the resource, the study of whether a field is promising or not might take a long time and involve enormous financial resources. Once the development starts, definitely the drilling would be the major cost, but then also the plant itself or the energy conversion method would involve equally large costs. And we are talking really about millions, for example, of major currency. A good example of what is the relative value of drilling costs compared to all other costs involved in studies, preliminary studies and exploration of the field. The costs of drilling, regardless of what exactly units we're using, definitely follow a somewhat cubic or logarithmic line. They grow a lot with growing depths. Direct use of heat from geothermal sources can be achieved in various ways, starting from low temperature applications. We don't need to talk much about those, and going through different types of heating applications, whether district heating or greenhouses or industrial processes, agriculture processes, and other. It is very easy to use geothermal heat once we have it, and it will usually present itself in the way of hot water. We will mostly concentrate, though, on the fancier way to utilize geothermal power, and that is to generate electricity with it. But that's the topic of the next section. Summarizing this section, we can repeat that definitely the most feasible way for commercial utilization of geothermal heat is to extract it as hot water, or why not definitely dry steam. If this can be achieved, it would be economic. And this is being done all around the world, where resources are available at achievable depths. What we exploit is actually the thermal energy stored in the Earth's crust. It is being recharged by the hot mantle beneath, but the recharging rate is usually much lower than the extraction rate we can achieve with a modern power plant. The available underground water table can be depleted also, and if this happens, it might have bad effects on the surface. Exploration and drilling are the most expensive processes in the preliminary study and reaching the resource. Direct utilization of heat for heat pump purposes is not a focus of this lecture.